Hello everyone. Myself Arvind and I will be speaking on smartphone annotation and screening tool for image labeling for artificial intelligence in 15 common retinal disorders. There are AI algorithm which can predict patient survival in 85% of cases based on data obtained by measuring the heart's electrical activity. The rapid development in AI technology requires ophthalmologists and computer scientists to have a good mutual understanding of the technology and the clinical practice to improve ophthalmological care. So, we did a world's first AI smartphone-based multicentric study for annotation and screening app development for 15 common retinal disorders at 15 retinal centers in India with 50 retinal specialists, IIT engineers, and optometrists. We initially begin by asking doctors to annotate the images using online platforms, but faced some of the following issues. Volume of the data increased over time and less portability because of desktop sites. Long images loading time due to weak internet connections, ever-changing disease schema, and as we kept on receiving some new data from hospitals we could not upload to these tools as it may violate patient data privacy laws. This led us to develop our own in-house image annotation tool. As seen in the video, adding in annotations for an image is pretty easy. View the image, magnify it, change the brightness, change the contrast as needed. Click on the relevant option, choose the extra details, and the annotation is saved. The analytics on the landing page shows the pending and completed images. The graph shows the maximum number of images stacked by the other users in real time, and gave the daily target settings. These imaging data sets are generally in the range of thousands and can be overwhelming for a single person. So we chunked them into sets, each containing 1000 images or less, which a grader can complete in 2 weeks. The issues mentioned earlier were resolved as follows. For faster image loading, we resized images into smaller size thumbnails with smaller memory footprint and still maintaining the visual quality. We leveraged the asynchronous capabilities of the browser and didn't load just 1 but 3 images preemptively so that the grader doesn't need to wait for the next image to load. The initial interface was basic and evolved based on the grader feedback. It is now designed on a decision tree structure to render the nested sub-classification and extra options. Finally, on the developer's end, we managed to Dockerize the entire application and deploy it using the Kubernetes platform. To ensure the highest standards of data security and privacy, our application is designed with Docker and Kubernetes, which reinforce our commitment to safeguarding patient data. All patient information is identified before it enters our system, aligning with the stringent regulations of General Data Protection Regulation and Health Insurance Portability and Accountability Act. We utilize robust, encrypted cloud storage to further protect this data. We have seen a total behavioral change where on the online tools the grader used to work only on the weekends, but on our tool we have a logged usage on all days of the week. Average time taken to label a single image reduced substantially. We validated the AI algorithm developed using annotations on this tool on some new testing data sets and found them to have really high performance scores. This strengthens our hypothesis that this tool is no different than the desktop-based tools and with added benefits of being portable and flexible. On the basis of satisfactory levels of verifications and validations, we are developing a smartphone-based app on a binary system of referable or non-referable decision for the retinal disease. In our pursuit to bring advanced eye care to the most remote and geographically challenged areas, we have developed an AI-equipped offline handheld non-mydriatic fundus camera. This device, along with a smartphone attachment for slit lamps, is designed to be the most cost-effective solution for diagnosis, screening, and referral purposes. As part of the Government of India's Netrayantiyodaya project, our handheld retinal scanner and digital slit lamp system are set to revolutionize eye care by making it more accessible and affordable for everyone. On this unique convolutional neural network-based algorithm on feeding a retinal image, it undergoes multi-level screening to provide a diagnosis in less than a minute to decide whether referral is required or not. Our system further enhances diagnostic precision by addressing 15 common retinal disorders. Each disorder is carefully analyzed by our AI algorithms to provide accurate and timely assessments. Also, we've implemented a sophisticated color coding system specifically for glaucoma detection. This system uses a visual spectrum where green indicates a healthy optic disc, while red signals a potential abnormality, enabling rapid and intuitive referral interpretation by healthcare providers. We wish to introduce more gamification label optimization to be used in telemedicine. With some minor tweaks, this tool can be easily adapted to work for other domains as well, such as anterior segment telemedicine, radiology, dermatology, etc. Our initial study got published in Clinical Ophthalmology and got awarded and recognized at 12 various international and national podium by the best in the field of ophthalmology. Conclusion: in our efforts in developing the AI smartphone-based screening tool, we are ensuring that critical eye care reaches even the most remote areas, improving outcomes for countless individuals. We remain committed to innovation and excellence, continually enhancing our tools to serve a broader range of ophthalmological needs. Thank you.